Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam then.
All right, so today we will discuss first on some example on lead compensator, and then we proceed with the next lecture, okay, next topic. Okay, so we are going to look at this question over here on the right. So consider a unity feedback system with a forward transfer function So can you see the slide? Okay, so consider a unity feedback system with a forward transfer function below. So GS equals K divided by S times S plus 5 times S plus 7. So design a lead compensator with a requirement of percent overshoot below 15%, while settling time TS equals 1.5. Assume compensator 0, ZC at -4. So if you are given this kind of question, you are going to first determine the dominant pole for the transfer function at the given overshoot and settling time. Okay, so if you have the slide from previous lecture, so we have some formulas given in the slide, such as the percent overshoot and also the settling time given here. So the first two slides that I showed to you here is important in order for you to determine the damping ratio, the natural frequency, and then the dominant pole. Okay, so let's determine these properties from the question. Okay, so the question says the percent overshoot is 15%. And settling time 1.5 seconds. So firstly, you need to determine the damping ratio using the formula from the slide that I showed earlier. Okay, so you just plug in the values in your calculator to get the damping ratio. So from calculator, you get damping ratio equals 0.6719. And then we need to determine the natural frequency from settling time. So settling time equals 4 over damping ratio times natural frequency. Okay, so you just plug in this value into your calculator to get omega n. So after you get both damping ratio and natural frequency, then you can determine the dominant pole. So if you look back at the slide from previous lecture, so the dominant pole located on this X here, and the real axis equals damping ratio times omega n, and the imaginary axis is omega n times the square root of 1 minus damping ratio squared. And then after you obtain the dominant pole, you can write the dominant pole in full. And then we can determine the compensator pole by finding the angles for each of the poles on this GS from this dominant pole. So maybe it's better if you can sketch the location of all of the poles. So this is the transfer function given to you. So you can plot the poles for this transfer function first. And then you plot the poles, the dominant pole, okay? So the dominant pole is somewhere, should be here. And also plot the location of the compensator 0. Okay, so we need to find the angle theta P1, theta Z1, theta P2, theta P3. And then we sum up all of them together. Make sure they are 180 degree. And then we know that this is a lead compensator. So for a lead compensator, we have the rules that says ZC must be bigger than PC. So your PC should be located maybe somewhere here, which means less than ZC value. So let's find the angle theta P1, theta Z1, theta P2, and theta P3. Okay, so firstly is theta P1. So it's this angle. So you can use 180 minus tangent minus 1 of this angle here. So it should be and then theta Z1. Then theta P2. And lastly, theta P3. And then you sum them up to make sure they are equals 180 degree. So using this formula, summation of angle 0 minus summation of angle pole equals 180 degree. So we have theta Z1 minus theta P1 plus theta P2 plus theta P3 and plus theta PC, which is the location of our compensator pole. So we want to find this value, then just substitute the calculation that you have done. So you get theta PC equals 332.34. So it is measured such that somewhere here. So you can take the mirror, okay, the mirror image of this angle, okay. So it's also the same with this angle here. Or simply 360 minus this value. So we know that the angle is measured here. Then we can use tangent to find the value of PC, okay, location PC. So theta PC equals 27.66. So it's the tangent minus 1 of 2.94 divided by PC minus 2.667. So PC is about 8.276. So after you get PC, then you can write down the compensator transfer function. Okay, so we get ZC equals -4 and PC is 8.276. But to write that, we need the gain K here. We don't have the gain K yet. So let's find the value of gain K before we can write the compensator transfer function GC. So to find K, we need to find the length of all of the poles N0 to the dominant pole. So maybe you can draw again. Okay, so what you need to do is you need to find this length. Let's say L1, L2, L3, L4, and L5. So let's find the length first. So L1 equals, just use theorem Pythagoras, okay? Pythagoras theorem. So you get square root of Okay, so after you find all of the angle, then you can calculate the product of the length. Okay, so if you still remember from lecture on root locus, then the product of length 0 divided by product of length poles equals 1 over k. So k equals the product of length poles divided by product of length 0. So the length of poles are L1, L3, L4, and L5, while the length 0 is L2, okay, because it measures from 0. So you can write first. Then you can use calculator to calculate the final value of k. So the value of k is 152 or 153. Okay. Then you can substitute the value of k, ZC, and PC to create. So GC equals 153 times S plus 4 divided by S plus 8.276. Okay, so the calculation is quite straightforward, but you need to be careful in determining the length and also the angle. Okay. So any questions before we proceed with a new lecture?
No, there.
Okay, so if you have no question, then we can proceed with a new lecture, which is the PID controller. Okay, so this is our last lecture. So the last topic is about PID controller. So previously you have learned about designing compensator to overcome or to produce some to improve the stability and the transient response of your given transfer function. So similarly, PID controller, the function is about the same, but the difference is that it has three different types of controller used together, which is the P, I, and D. So after completing this lecture, you will be able to understand the purpose of P, PI, PD, and PID controller. And then apply tuning rules in designing a PID controller using Ziegler-Nichols method. So let's look at some theory about PID controller. So why we need PID controller? So let's say the variable being controlled is the output of the controller. So let's say U is the output of the controller, and the output of the controller will change in response to a change in measurement or set point error. So if you have an error E, which is obtained from this summing junction, so the controller will uh, adjust the value of E so that it produce an output U for the plant. Okay, so the plant is the system that you want to control, and the controller basically evaluate the error, the measurement error, and do something. Okay, either reduce the error, or in case you want to increase the error, for example, you can do that as well using the controller. So a PID controller consists of three different, I would say, controllers. Okay. So firstly, we call it the P controller or the proportional controller. So a proportional controller basically has the gain KP, only KP. And then the second one is the integral controller, which consists of Ki, the gain Ki, divided by S. So the transfer function for integral controller is Ki divided by S. And lastly, we have a derivative controller, in which, in this case, the transfer function for derivative controller is simply the gain Kd times S. So you can sum of all of this together to get Kds squared plus Kps plus Ki over S. So this is the final transfer function of a PID controller. So in last week's lecture, we have seen that in this topic, we only use the PID controller. So before we go into detail about PID controller, let's revise a bit on what are the system variables that you want to control. So we have the overshoot here. So the overshoot is usually you want to control. Okay, so you want to reduce the overshoot so that the system will produce a smaller overshoot. Another thing that you want to improve in a control in a system by adding a controller is improving the steady state error. So usually you have some error in your system, so you want to reduce the steady state error. So preferably you want to eliminate steady state error to make it equal 0. And then lastly, the rise time here. So the rise time, you want the system to have a smaller rise time so that it responds quickly, so that the system responded quickly to the input and reach the steady state as quick as possible. But if you have a system that has smaller rise time, you will definitely have an overshoot in that system. So each of these parameter, rise time, overshoot, and steady state error, when you reduce one of them, it will affect the other, it will increase the other. So in real life, you cannot have a system that eliminates all of these three at the same time. So for example, here, you want the system to follow this black line here, but you either can get the system to behave as in the first garis putus here, or the second one here, which has an overshoot. So if you reduce the rise time, then the system will have overshoot. And it is stable, but it will take some time before reaching steady state value. It will oscillate, okay? Oscillate before reaching steady state value. While the second system here, the rise time is very, very slow, very long, but the system has no overshoot. But the system will respond very slowly before reaching the steady state value. So you want to improve the system, but you cannot get the black line here. But the best system response that you can get is the red colored line here. This is the best that you can get, which meets all of the criteria that you want, okay, which reduce the overshoot, reduce steady state error, and also reduce the rise time. So let's look at some example of controller design. Okay, so let's say you are given this translational mechanical system. So you can derive the transfer function, and this transfer function is your plant, okay, your plant system. So you want to control the plant by adding the PID controller here, Kp plus Ki over S plus Kd times S. So let's say if you don't put any controller, so you just use the plant. So this is the time response of your plant without the controller. So as you can see, the final value here, the value at steady state is 0.05, in which the final value is actually 1. Okay, you must reach the value 1 for this system, but for system without any controller, you only get final value equals 0.05. In this case, the steady state error is 95%, which is very, very large. And the settling time is about 1.5 seconds. So here you want to reduce the steady state error because the steady state error is very large, 95%. So you can add a proportional controller, Kp. So only add a Kp, and then you tune the system by choosing Kp equals 300. So what happened here is that if you put Kp equals 300, then the system will have an overshoot, but the rise time and steady state error is reduced. So if you look at the steady state value here, it reaches almost 1, which is about 0.95. So just now, before adding controller, you get 0.05, which is about here. So now the steady state error has been reduced, but you introduce an overshoot in the system. And the other things like rise time and settle time has been reduced. So the problem here is that you introduce overshoot to the system when you put a proportional controller. So this is the figure when you use different Kp value, different proportional controller value. So if you use 100, the overshoot is less, but the steady state error is still bigger. But if you use a bigger Kp, you get more overshoot, but steady state error is reduced more. So and also reduce the steady state error. So how about we add another controller, which is the derivative controller alongside with Kp. So we choose Kp equals 300 and Kd equals 10, and then we plot the time response. So here we can see that the overshoot is reduced slightly compared to the previous example, and the settling time also reduced. However, if you put Kd, the effect is very small on the rise time and also on steady state error. It doesn't affect both of these much, but it reduces overshoot and settling time. So here are the effect of choosing different Kd value. So if you use Kd equals 10, you get overshoot about 1.1. And if you increase Kd equals 20, the overshoot is reduced more. But you can see that the steady state error, the steady state value is about the same, 0.9 something. So it doesn't affect steady state error. It only reduce overshoot and also settling time. So now we replace Kd with Ki over S. We add an integral controller alongside Kp. And we choose suitable value for Kp and Ki. So when we choose Kp equals 30 and Ki equals 70, we get the system that has reduced rise time, but with an overshoot. But the above response shows that by adding Ki, we can eliminate the steady state error. So if you look at this line here, the line which is steady state value equals 1, which means that the steady state error has been reduced. So if we change the value of Ki from 70 to 100, we can see that the overshoot is increasing, but the steady state error has been eliminated. Now, lastly, we add all of the controllers at the same time, Kp, Kd, and also Ki. When we add all of this together, we can see that the system has no overshoot, has faster rise time, and has no steady state error. So each of the controller has its own effect, like P, PD, Pi, and PID. So depends on your needs, you can choose suitable controller to suit your system requirement. So this table summarizes the effect of each controller. So if you have Kp, if you increase your value of Kp, then rise time will decrease. You increase overshoot of the system, but it has small effect on settling time. But increasing Kp will decrease the steady state error. But if you have Ki, if you increase the value of Ki, it will decrease the rise time, but increase the overshoot, and also increase the settling time. But the best about Ki is it eliminates the steady state error. And lastly, if you have Kd and you increase the value of Kd, it doesn't affect the rise time and steady state error, but it affects the overshoot and the settling time of the system. So the more Kd value, you get less overshoot and less settling time. So each of these has its own effect on the system. So how to determine the value Kp, Ki, and Kd is by using tuning, by tuning the PID controller. So usually the transfer function of the plant of a control system is very complicated. So this is similar as last week about compensator, when we want to why we want to design a compensator, because if we want to improve the system stability, we cannot change the plant. So we need to add something that improve the plant transfer function. So this can be done by adding a PID controller, which we need to tune the values of the Kp, Ki, and Kd, which can be done by trial and error. So there's one rule which is proposed by Ziegler-Nichols, which is used for tuning the PID controller. So there are two Ziegler-Nichols tuning rules, but in this lecture, I will only explain to you the second rules of Ziegler-Nichols. So we skip the first rule. So we go straight to second Ziegler-Nichols tuning rules. So the second Ziegler-Nichols tuning rules, first you need to set the integral and derivative gains, which is the Kp times Ti and Td here. We need to set Ti and Td equals 0. And we let the PID controller depends only on the proportional gain, only Kp. And then after that, we increase the value of Kp until a critical value Kcr, at which when we increase Kp, then the system will exhibit a sustained oscillation with a period of PCR. So we increase Kp until you get the system to oscillate sustainably, meaning that the system will become marginally stable, which means it keeps oscillating without having an increase time response or decrease in time response. So when the system oscillate sustainably, then we can determine the PCR or the period of oscillation, and also the frequency of oscillation FCR. So it's basically determine PCR and FCR at marginally stable system, which we can use JW axis crossing concept, or by using Rapp-Hurwitz criteria that you have learned in previous weeks. Then after we determine the right value of Kp and the value of PCR, we can use this table to further determine the actual value of Kp, the actual value of Ti and Td. So we use a PID controller. So for a PID controller, Kp equals 0.6 kCr, Ti equals 0.5 times PCR, Td equals 0.125 times PCR. So if you want to use P and Pi, then these are the values. Okay, but we focus only on PID controller. So let's look at an example how to apply Ziegler-Nichols tuning rule. So let's say you are given this controller or this system. You have a PID controller GC here, and the plan 1 over S times S plus 1 times S plus 5. So you want to design a PID controller using Ziegler-Nichols tuning rule. So firstly, what you need to do is you need to assume that the system or the PID controller is only made up of Kp only Kp. So you neglect the value of Ki and Kd. So setting Ti equals infinity and Td equals 0, or simply Ki and Kd equals 0, we can obtain the closed loop transfer function Kp equals S times S plus 1 times S plus 5 plus Kp. So simply make Gc equals Kp, then simplify the block diagram to obtain this closed loop transfer function here. And then the value of Kp that makes the system marginally stable, you need to determine this value, Kp at marginally stable system, using Rapp stability criteria. So you take the denominator, expand and rewrite in terms of full complete polynomial, then create the Rapp-Hurwitz table. And then similarly use rho S1 to get the value of Kp. So you get Kp equals 30. So Kp equals 30 is the critical gain KCR, the value of KCR at which the system will oscillate marginally. Then from the KCR value, you use rho S2 to determine the period of oscillation. So from rho S2, you can write 6S squared plus 30 equals 0. And then you get S squared equals minus 5. So S equals plus minus square root 5J. So this is the J omega crossing, or the value of S at marginally stable system. And this value here, square root 5, is the frequency of the oscillation. So here we get the frequency equals square root 5. So you need to determine the period of oscillation. So the frequency that we get is in terms of radian per second. So you need to determine the period by considering the 2 pi. Okay. So omega equals to pi f. So f is 1 over period. So period equals 2 pi over omega. So omega is your square root 5. Okay, so you will get this calculation here. So after you find PCR, the period of oscillation, then you can use the table that I showed earlier, this table, and substitute the value of KCR and PCR to obtain KP, TI, and TD. So the example given to you, calculated KP equals 18, TI equals 1.405, TD equals 0.35124. And then you use the value of KP, TI, and TD to substitute into the controller transfer function. Okay, you rewrite the final. Okay, so fairly straightforward. You need to first assume the controller is made up of KP, and then find the closed loop transfer function, generate route rate table, find KP at marginally stable, then find the value of PCR, the period of oscillation, and then determine KP, TI, and TD, then determine the final transfer function. Okay, any questions before we proceed for tutorial?
Okay.
Okay, so let's look at tutorial 13. So there are two questions here. So question number one is using the first method. So this will not come out in final exam. So the tutorial question number two is about second method. So it will come out in final exam. So let's look at this question and how we can answer this. So a closed loop system is shown below. If the plant has a transfer function given by GS, so find the critical gain KCR when the system is marginally stable. So firstly, we have GS equals 1 over 2s power 4 plus 5s cubed plus s squared plus 2s. So what you need to do first is find the closed loop transfer function of this system, assuming the controller is made up only Kp. So closed loop transfer function equals okay, and then take the denominator and generate the route rates table. Okay, so after you generate the route orbit table, you use the row S1 to determine the critical gain KCR. Okay, so this is the value of KCR. Then from here, you need to determine the period of oscillation. So you use the row S2 to determine the J omega axis crossing. Okay, so we get the frequency equals square root 2/5. So to get the period, the critical period, it's simply 2 pi over omega. Or you can use calculator. So we get PCR and KCR. Then we use the table to determine KP, TI, and TD. So KP equals 0.6 times KCR. Then TI equals 0.5 PCR. And TD is 0.125 times PCR. So after you get all KP, TI, and TD, then you need to rewrite the transfer function for the controller. So GC GCS equals KP times 1 plus 1 over TIS plus TDS. So just substitute back all of the values. Okay. Or you can simplify if you want. Okay. So this is the controller that will control the plant to get the system to have the best performance that has no overshoot, smaller rise time, and also no steady state error. Okay, so that's it for today's lecture. Any question before we end our class?
So far, no, brother. We practice.
Okay, so that's it for our class for AC this semester. And you still have 2 more projects to submit, project part 4, which is this Wednesday. and also part 5. I think part 5 I will give you until Sunday. We'll see about that. And later on, maybe next week, I will let you know what topic that will come out in final exam. And that's it. That's it for our class for this semester. So if you have any question regarding the topic that you have learned, feel free to WhatsApp me, and I will help you as much as I can. Okay, so thank you very much, and see you in next semester, inshallah. Assalamualaikum and goodbye.
For quiz 5,
I will let you know when quiz 5 is released. Okay?
Kira dah.
Okay, thank you very much. Assalamualaikum and goodbye.
Thank you, Dr.